MOSFET theory story. So PMOS is remaining in the class to complete this device. So one time I'll write everything in the board, PMOS diagrams, all these things, you copy it. After completion, I'll just give you an idea for you how PMOS concept happens. Just please note on it. I'm not talking anything, please note on it. PMOS, again, MOSFET theory story. So PMOS diagram, please, depletion enhancement. I'm trying to develop here, try to see. Please copy all these things, what I'm writing. So please note on all these things. Only two models. First, we must get the visualization to write the mathematics on this. This is called PMOS structures. Why the batteries are connected like that? You can see the reasons behind this by this negative polarity. The body is connected to negative. Here, electrons will get attracted towards the channel. The holes will get attracted towards the body terminal, so that the current will decrease as VGS increases. That is the story. As VGS increases, here ID current will decrease. That is called depletion effect. Same manner we can draw here PMOS enhancement. MOSFET. Now if you can write these points, it is easy for me to teach the mathematics for P channel. So you can see clearly the graphs one time. Your VDS graphs came in the second quadrant. That point please try to understand. That means you will get current saturations in the negative side here. Okay, current saturations will come in the negative side for PMOS. And VGS will come in the positive side for depletion techniques. Therefore VT will become positive for depletion. VT will become negative for enhancement. This graph will tell you all the conditions we are writing in our class. Okay, that's why please try to note down clearly these points. Now we'll see the mathematics of PMOS to end up this concept. We'll start the envelope part from here. Yeah, Akshant, silicon dioxide layer is present, but I have not written it. You can, it's a default, you can see the silicon dioxide layer. There will be compulsory silicon dioxide layer. There will be silicon dioxide. It's a default. You can have a silicon dioxide. There will be silicon dioxide layer. In MOSFET, there is a word oxide. Compulsory silicon dioxide will be there. By chance, if I don't write, okay, default you can think there is a silicon dioxide. Summarize, the class has started at 2:40 exactly. Because now only I have written all these things in PMOS diagrams. You just copy it. We'll start our journey from here. These diagrams will explain for the student why VGS is negative, why VGS is positive. Okay, why it is happening. These conditions will explain. Here, who will connect to body positive, source positive, then only this mechanism will happen. As VGS increases, ID will increase. Who will connect to body negative, source negative, this mechanism will happen called ID will decrease with respect to VGS. That is the meaning of the sign techniques. Whatever you like, we are not applying. According to the mechanism, the batteries are suitable for depletion and enhancement mode. Okay? Now we got clarity on the graphs. Now we can start doing the mathematics now. Let us understand how to analyze a graph now. Operating regions will write in the same manner. please tell me so that I can start the mathematics behind this. Will complete. Swati completed. Good. The remaining students, if you have completed, we can proceed the concept. Just 1 minute, I'll wait. Please complete it. An enhancement type, Japanese is asking a question. ID versus VGS. Okay. After threshold voltage, the ID current will constantly increase. Yes, here what happened is the current will decrease. If you go like this reverse bias voltage it is. Okay. The current will decrease. But if you are going for this side, VGS are becoming a forward effect for it. So it will try to rise, he is telling. So below this you have to take 0. Below the negative values you have to take it as on condition here. Okay, Arpita, please note down it. I'll give time for you, 2 minutes. Please write properly first. This graphs will help you a lot to understand the conditions today. It will help you a lot to understand conditions. Otherwise, you'll get confused with the equations now. So that means if anybody apply any value greater than threshold voltage in this PMOS problems, any value greater than threshold voltage, your MOSFET will be off here. Any value, if you give below threshold voltage, you will get on. It's a reverse concept. If you're greater, you will be off. If you're less, you will be on. Because you have to apply the negative values this side, not the positive values. Okay? That is the meaning what I'm saying in the graph. So let us start analyzing the operating regions, PMOS operating regions, we'll see. Arpita, I think it's completed for you. Let us start. Let us start. Okay? I've given a good time for you. Let us start now. PMOS operating regions. PMOS operating regions. Keep the heading. PMOS operating regions. Here the graph should be reverse graph you have to understand. Your VDS will come always in negative side in PMOS. So your study graph should be like this. This is your study graph. There's a boundary here. This is your VDS set, which is equal to VGS minus VT. Now you are studying in this manner. This portion above 0 up to some portion we see linear. So we'll take this as equation 1. This is the first region, region 1. And second region we have is sublinear graph, just like previous topic. So we'll take this as equation, this is your region number 2. And we'll go for this portion. This is your region number 3. So you can explain all these 3 regions with equations. So you can see the equations how to write. Step 1, we are going for step 1. Step 1. The first region we call it as linear region, or we can call it as ohmic region. And some student has been given a name for this. That is also correct. Okay, deep triode region. There's some more names we can write like this. There's only orally we are speaking the names. We can call it as a deep triode region. That means a triode effect. If you go in terms of deep, you'll see a linear region. So linear, ohmic, deep triode region also we can speak. But most of the times they never use this word. Ohmic or linear you'll see in the exam point of view. That's only for our convenience. They're writing that word deep triode region. Okay. Deep triode region. So next the conditions, if you see the conditions. If you see the conditions for this, you'll get confused here. See correctly. VGS should be less than or equal to VT. So see this condition, very interesting condition. Previously when VGS is greater than or equal to VT, your MOSFET is on in NMOS. But here what happens is a VGS should be less than or equal to VT we have to make. So what is the reason for that mean? Simple logic. VGS should be less than or equal to VT. What is the meaning of less than or equal means? You can see. A graph dekho. If you are less than VT, you are on. If you are greater than, you are off. It should be less than, you are on. Greater than, you are off from the graph. Here also you can see. Less than, you are on. Greater than, you are off. Okay, this graph, that's why I have written the board clearly. So that's why less than you must be always. So this point is very important. Less than you will be on, so that the VDS should be 0 volts or small millivolt, negative millivolts should be required. Because VDS is a negative voltage. It should be minus millivolts is required. Means somewhere here, millivolts region, which is a negative millivolts. At that time, you can have an equation called ID. It is nu P will come, because you are talking about PMOS. Holes mobility and electrons mobility will not be same in electronics. That's why nu P are taken. Nu P, same. Capacitance, same. W by L, same. VGS minus VT into VDS. Somebody asked me, sir, how to remember these formulas. You have no need of remembrance. Daily, you are going to use these equations in analog electronics. Every question will try to solve with these equations only. So it's very easy to remember. One is mobility will be there. One is capacitance will be there. One is W by L. They're all called standard terms, which we never forget in our life. And VGS minus VT will be the order voltage and VDS. All are one individual terms will be recorrect in your mind very easily. The next one we have is step 2. In place of mobility of electrons, you have to take mobility of holes. That is the difference here. Second region, we can call it as triode region. Or we can also call it as sublinear region. We can call it as sublinear region. What is the conditions? What is the conditions here is? Conditions. VGS should be less than or equal to VT, it will be on. And VDS should be greater than VGS minus VT. If you see clearly here, in the previous NMOS we have taken VDS less than VGS minus VT is triode. But in this graph, if you see, if you are more than VGS minus VT, you are on. You are in triode. A graph is mathematics. If you are greater, you are in triode. That's why these indications will confuse the student. That's why graph is very important to visualize why the person is saying greater. Okay, so this is less, this should be greater. Therefore, what is the current relation here is ID is equal to UP Cox W by L into VGS minus VD into VDS minus half into VDS square. So this is your equation. This is one equation. Keep these results in brackets. This is one equation. All are looking similar equations. No need of any tensions. Only thing is new piece will be changing in the MOSFETs. The remaining things are same. Satyam Satyaprakash. If VDS is 0, what happens here? If VDS is 0, your current is 0. The current started from there. Okay? The current started from there. 0 onwards, the current started. So you can say in general, 0 or millivolts you can tell, no problem. Exam is 0 volts when you get, but you are on, you can say it is on condition. Okay? Cutoff if you want, suppose nothing is there. This condition will get failure automatically. The first voltage, if you are less than become greater than, your total transfer is off. Nothing to check the second one. But in general, ohmic region, we say 0 to millivolts. Yes, Ananya, maybe today class will go up to 5, 5:30 or 6. It will not go beyond that, don't worry. Okay? Maximum 6 or 6. 6 is the maximum I'm expecting to complete the task. Ojaiga concepts, just only these equations if you complete. Doing analog part is very easy. Okay? To complete Ojaiga, don't get tension. So ID is equal to nu p Cox W by LP. Below this boundary, you are in current saturation. Okay, formula you cannot see, just I'm moving it, you can see. So what is the last one here is ID relation, you can write it as half into UP Cox W by L to VGS minus VT whole square. This is your current relation. This is your current relation. You can add one more step in this concept is step 4. Step 4 also you can add. Last step for you. Suppose anybody want cutoff in the class. If you want to know cutoff, the transistor should be in cutoff. The condition is very simple. A VGS should be greater than VT. If the VGS becomes greater than threshold voltage, your transistor will be cut off, such that your ID becomes 0. So you can add one more concept, cutoff technique also. Cutoff failure, we don't need more than one value. So Majender, I think today workbook maybe not complete. Tomorrow morning will complete. Workbook tomorrow, passing problems, all these things takes 1 hour class. So after that we'll start doing the remaining part tomorrow. By tomorrow we are closing the subject of MOSFET. Okay. Today maybe theory part will be completed. Total issues, design part, everything I'll cover for you. Tomorrow morning freshly we'll complete the workbook problems based on these 2 modules. Okay. Tomorrow morning we'll complete this remaining points. Just today my job is content we have to complete today. Okay. Samresh, I think a lot of time for it here. Again, going back is not good. Okay. Other students will get disturbed. In the recording video you can see that. Okay. Please you can see the recording video. Just write the PMOS equations and start the class today. We are ready to start the analog class now. Till now we have done only device class. Taking a lot of time for device part. Nothing is there in the previous slide. The previous slide, nothing I explained. These 2 diagrams I explained. That is called depletion type and enhancement type diagrams. If you miss anything in the recording video, you can note down. And if you can go back to your slide, this is your equations we studied. In your NMOS also you can take step 4. In NMOS also you can write. Go back and write in NMOS that cutoff if you want. In NMOS also you can add that step 4. Cutoff if you want. VGS should be less than VT. Whenever you see like this, your gate to source voltage is less than threshold voltage. In NMOS it will be cut off. So ID becomes 0 directly in this problem. So you can add this point in your NMOS question, which I have not written in the previous content. Please add it. Go back and see your notes and write on this as step 4. This is for NMOS. And now presently we are dealing about PMOS. This is for PMOS. So NMOS के लिए VGS should be less than VT for cutoff. For PMOS is VGS should be greater than VT. You will be cut off. Okay, that is the situation. Okay, Majender, definitely. Who has missed the first slide? Okay, at the end of the class completion or in the break time, I'll just break after this. At the time, I'll keep that slide. You can copy it. Okay. Samresh also is asking the previous slide. Let's keep that slide in the break time. Okay. Please give the question numbers for tomorrow to be done so that we can try at home. Definitely, who is this? Sumanta, definitely. Whatever the questions you can solve, I'll give the numbers for you tomorrow. Just try it. Tomorrow I'll solve it. Is it okay? Definitely. At the end, I'll give the question numbers. You just try it. How many questions you can do it. Tomorrow you can do parallel with me. The questions. So please copy all these 4 steps. Just I want to know what is current saturation equation, today process characteristic equation, and what is GM for MOSFET. Till now we have been covered GM for BJTs, GM for GFETs, now GM for MOSFET. That also will complete. Then we'll stop this analysis. I'm so happy that total device part is ready now. It's easy for me to teach analog portion. Yeah, further at the end I'll give all the question numbers, don't worry. You can try to solve one time. Tomorrow we'll see the questions. So please tell me if it is copied. Last step I'll explain you about my GM concept. I'll explain final step. With this total content is ready for you. Roy is telling covered, completed. Please tell me if you have completed the last slide I'll explain to start the today analog class. I'll complete the testing, then I'll use small break for you. After that, passing class. That is the last today. Copied? Great. Okay. So let us see the final step today called transfer characteristic equation. Transfer characteristic. Transfer characteristic equation of MOSFET. So what is the transfer characteristic equation of MOSFET? If you want to learn transfer characteristic equation of MOSFET, if I take an NMOS or PMOS, any one example is enough. Suppose NMOS if I take, your ID is equal to half into nu n Cox W by L VGS minus VT whole square. This is your equation actually. Half into nu n Cox W by L VGS minus VT whole square. Now if I differentiate with respect to VGS, that is a derivative of ID by derivative of VGS, which is called GM, transconductance, which is nothing but the 2x we have to take, x square, 2x is the derivative. So 2 into half into nu n Cox W by L into VGS minus VT. So we'll get like this. GM formula will be written like this. Okay? So this will be 2 to cancel. So GM is coming to be nu n Cox W by L VGS minus VT. So this is about your GM formula. This is about your GM. Nu n Cox W by L VGS minus VT is called GM. But there are some notations here. We'll write some notations here. K and dash in the problems. K and dash is nothing but nu n Cox. So we'll make a product of mobility into capacitance of oxide layer. We have given some indication for that as K and dash. Yes, Arpita. ID will be 0 for the cutoff regions. Kn is called nu n Cox. The unit says milliampere per whole square. This is called as process transconductance parameter. We call transconductance parameter. We can call this as K and dash. We can call it as this one. Process transconductance parameter means this nu n Cox is a function of GM. You can see in the port. Mobility capacitance is directly proportional to your GM. But mobility capacitance is not depends on user. It depends on the manufacturer. So that's why they are called process control parameters. So it has given some name K and dash in the classes. Exams mean they'll say the word K and dash. You have to mean that nu n Cox is given in the problem. Otherwise they'll define it also sometimes. If they don't define, that meaning is nu n into Cox. And there's one more letter which will confuse the students. Kn. Nu n Cox W by L. Kn is different. K and dash is different. Kn means you are multiplying with W by L also. For every MOSFET we have W by L is different. Just like our betas of the BJT transistors, in MOSFETs we have W by Ls. Each transistor we can differentiate by W by L ratios. So Kn is not only depending on process, it is depending on my MOSFET parameter. That's why I got the name as MOSFET transconductance parameter. This is called MOSFET transconductance parameter. So sometimes Kn value, sometimes they can write nu n Cox W by L in the exams, or sometimes they'll speak this letter as Kn as half into nu n Cox W by L. They try to define like this. Kn sometimes half extra they'll add, sometimes they'll remove half. Examiner what they have given, you have to take according to that. Nu n Cox W by L, you take that as Kn. If they give half into nu n Cox, that you take it as Kn. According to the given information you can take. Suppose they are not given anything, then what you take means this is called default. Your Kn, then default I'll understand that is half into nu n Cox W by L. Means this total term I'll define it as Kn. This total term I'll define it as Kn. In GM terms, this total term I'll define it as Kn. So like this we have two different variants. So Kn can be written in two manners. Okay? Jahnavi, what is that? Dimension MOSFET is depending on ID. Rahman here, L means length of the channel here. Channel length may current depend होते ना. Width of the channel, length of the channel may current compulsory depends. So W by L will play a key role to get the current ID. And somebody is asking units are not properly. You are seeing? These units are, can say milliampere per volt square or amperes per volt square sometimes. Milliampere per volt square. These all units are same. Milliampere per volt square or amperes per volt square you will get. So this completes the total knowledge about GM concept, transconductance, how to find out. Satya Prakash, here half from Kunia here, this he can define it as Kn is telling. Because in ID term I can take this total as Kn if I am speaking about this story. In GM half is missing, we can call this three terms as Kn. So Kn they will try to define for you. How much we have to take, half you have to take or not, they will define. According to that you take one and solve the question. Okay? If they don't give anything, you feel that Kn should be this one. Half into nu n into Cox W by L to Kn marker, try to solve the problems. The two options are there for us, Kn. Sometimes they can go off, sometimes they can remove it. Satyam, no need of any derivations here. Okay? Derivations, everything equal. Just learn the equations and complete the analog part. You'll be happy to complete the subject. Calculus students को derivations नहीं चाहिए. Unnecessarily you are increasing your content. That will disturb your practice of analog concepts. Only thing is how to apply it and how to do it is important. अब derivations करके ये concepts को भूल जाते हैं आप. Okay? Main equations को practice करो. How the sir is teaching, what is the art of practice that you practice it. If really derivations are required for exam point of view, then definitely I'll explain now. You're not a conventional student also. Nobody will ask you derivations in optical questions. Again, Pooja Prabhakar is asking what is the physical significance of transconductance. I already told you in the morning itself. The physical significance of transconductance GM. Therefore, I understood that BJT will work as a strong amplifier compared to a MOSFET. That is due to this calculation part. Okay, that is the significance of GMs. So let us start our journey. First class is completed. Topic 1 I completed till now. It is now 3:30. Topic 1 is completed. That is called basics of JFET and MOSFET is completed. Now we are entering to the concept of testing. Hardly 1 hour will complete the testing part. Okay. Analog main module we are starting now. Testing designs. Somebody does again straightforward will ask you the question. Immediately you ask, why sir MOSFET is having less GM? Immediately ask a question. What take the समझ में how could be? Mobility, capacitance is depending everywhere. Capacitance values are very, very small values. Capacitance will not be a strong value in your MOS capacitors. Mobility is a small value. And W value is a small value. All these components will decide the GM for you. Whereas the components are very less coming for you, I think your GM is not coming much. Okay? Because it's entirely depending on these three products. So your capacitors, you know that there will be an order of microfarads, sometimes nanofarads, sometimes picofarads. Then if it is coming in pico or nano, I think the Kn value is very, very small. Due to that reason, you are getting less GM. It's not required to ask me. By seeing the board only, you can understand that stories. Okay? So let us start our second topic journey. That is second topic I'm starting. That is called MOSFET testing we are doing. MOSFET testing. MOSFET testing. Generally, MOSFETs will test only in one mode. Enhancement mode will test. Because main applications we have is enhancement mode of operations. That's why most of the times my industry is an enhancement mode. So how to make MOSFET enhancement mode testing is important. So today I'll take some examples to teach you different testing parts now. So we'll start with the first example is cutoff testing, how to do it. I'll explain with examples. Cutoff testing, how to analyze is the first concept. Okay, cutoff we are doing. Cutoff testing I'm doing. We take cutoff alien. Example 1 will do it. Example 1. Two examples I'll explain NMOS and PMOS examples. Example 1 is like this. We take these values 1.5 volts. This is 1 volt and this is 2 volts. Given VD threshold voltage is 0.8 volts. This is one question we'll try to analyze. Side by I'll do another question. Two examples I'll explain for each region so that you'll understand each topic now. This is example 2 for the cutoff region techniques. Given threshold voltage for this problem is minus 0.8 volts. These are PMOS questions. This is 2 volts, this is 0.5 volts, and this is 1 volt. So these two questions I have designed for cutoff techniques. These two questions I have designed for cutoff techniques. Let us understand how these two questions are in cutoff. One is PMOS and one is NMOS question. We just draw these two diagrams and keep small gap. Hardly takes 2-3 steps to solve the questions. Okay? So we keep some gap here and note on the second circuit and be ready to calculate these two circuits. The first circuit I'll explain you, then remaining you can do yourself, these concepts. Okay? So first if you see the circuit 1 here, in the exam, the first point what the theory you have to take is, you have to write where is the gate, first identify these things. This is the drain, this is the source. Just identify the terminals. But if you go to PMOS, sometimes they'll take a source in the top, don't get confused. Source they can take at the top, so this is source actual. This is drain, this is gate. PMOS can be drawn like this most of the times. Source they will show higher potential, drain they will show lower potential. That's why source they will take top, drain they will take bottom sometimes, so be careful in identifying the potentials in the class. Our target is, we have only two potentials here. One is VGS potential will be there, and one is VDS potential will be there. Correct? The first point we have to test whether the MOSFET is cut off, whether it is off or on. First we have to check. That will be decided by the VGS voltage. If you see VGS voltage here, which is VG minus VS in the problem, the gate voltage is given as 1.5 minus source voltage is given as 1 volt. So answer is 0.5 volts we are getting. But the actual threshold voltage is given as 0.8. So your VGS is coming less than threshold because 0.5 will be less than 0.8. Therefore you can decide that your M, that is MOSFET, is in cutoff. You can decide the problem. If MOSFET is in cutoff, your ID current will be 0. So only by one single step you can answer this question. Your ID will be 0. This is the best example to teach you how a cutoff question they will design in the exams. This is a cutoff question. Similarly here also you can do it. The VGS we have here now. VDS we have here. VGS and VDS you consider. So here what is the VGS value if I solve it? It is a VG minus VS. VG is 2 volts minus 1 volt. So it is becoming 1 volt. So gate voltage they have given more than the source voltage. So VGS came to positive side. But we know that your VGS, if you are less than threshold voltage, less than or equal to threshold voltage, you will be, less than. When VGS is less than threshold voltage, you will get on in the PMOS. VGS is greater than threshold, you will be off. So I think should be greater, you will be off. I think your answer came greater, you can see. VGS came as 1 volt, but threshold voltage is minus 0.8. So you are greater you got. Here less if you get off, here we will get greater you will off. So this is design. Your MOSFET is in cutoff. MOSFET is in cutoff. So ID will be 0. So this concludes my first analysis. Example number 1 is completed in our analog electronics. So till now how much work you have done, it makes you more enjoyable to study this MOSFET design classes. So everybody can be cool to understand this concept. So cutoff region technique is completed. We have 3 more regions to test like this. So please complete it. Maybe half an hour we can complete this area. Within half an hour I can complete, I'm thinking. testing VDS is enough to test the circuit. Okay, cutoff के लिए both batteries are not required, both drops are not required. Only one VGS is enough to tell your transistor is in cutoff or not. Yeah, it is completed. I'm expecting. So we'll go for the next example. So hardly one step question, correct? Takes only one step to solve this type of questions. Let us go for example number 2 called as ohmic region analysis will do it. Okay, we'll go for ohmic region. Chalo then, most of the students are completed. Next we are going for ohmic region. Second concept, ohmic region analysis. Ohmic region. Ohmic region. You take it as example 1 for this. Example 1 I'm doing problem designing. You can see how to design this problem. Take a threshold voltage as 0.5 you take for this problem. Given threshold is 0.5. This is given as 1.5 volts. This is given as 0.5 volts. This is also given as 0.5 volts. Take this as example 1 and do some analysis here. And example 2, I'll create with PMOS now. PMOS design. Threshold is given as minus 0.5 volts suppose. The MOSFET, PMOS, you can see. This is a PMOS question. How much is the value says? 1 volt, 2 volts, this is 2 volts. Try to check these answers with your knowledge. Please try to solve these two questions. Before I am doing, you try to solve the questions. Okay, you got an idea how the path I am going to complete the concepts. So let us check it. First, what is it? Points should be practiced correctly. This is gate, identify the points. This is source, this is drain. These are the points. Here gate is here, source is here, and drain is here. These points you write clearly. Okay. The next we have is VGS is here, and VDS is here. So first we'll find out what is VGS value to check that whether the MOSFET is on or off. VG minus VS. This is 1.5 minus 0.5. Answer is coming to be 1 volt. VGS we are getting 1 volt we are getting in the class. As VGS is 1 volt, can I say that VGS is coming greater than VD? VGS is greater than VD because VD is 0.5. This is 1 volt. So I can say that your MOSFET is on, I can decide. I decided with this knowledge, MOSFET is not off, it is not cut off, it is on. Whenever MOSFET comes into on, it has 3 regions. It can be ohmic, it can be triode, or it can be current saturation. To confirm that, we have to find out the VDS value. VDS is nothing but VD minus VS. It is 0.5 minus 0.5, answer is 0 volts. Whenever the VDS comes 0 or close to 0, we say your MOSFET is in. MOSFET is in ohmic region. This is the style how the questions will be. MOSFET is in ohmic. So in the exams they'll design VDS value as 0 volts. Therefore you can say the MOSFET is in ohmic because you are very close to 0 is linear. In that manner you can tell the answer. A similar manner you can do here. This is VGS. This is VDS. First find out the VGS here also. This VG minus VS is 1 minus 2. Answer is minus 1 volt we are getting. In the PMOS the answer is coming minus 1. Whenever you get minus 1, your VGS, if you are less than VD, you are on. This is minus 0.5 given. This is minus 1 we got. I think minus 1 will be less than minus 0.5. Therefore, this condition is satisfied. So you can say your MOSFET is on. MOSFET is on. If you are less, you are on. MOSFET is on, you can confirm with PMOS design. Okay. Then what is VDS? We can find out. VDS is VD minus VS. Your VD is 2 minus 2. Answer is 0 volts. So MOSFET is in ohmic region, you can say. So you can say this is the way how to check the ohmic region concept. This completes my idea number 2, how to check the MOSFETs in ohmic effect. So we will study my notes clearly. These questions doing in the exams is not a big task for you. Sometimes exams may linear region they can ask you, or ohmic region, both are same. Linear or ohmic, anything you can speak. Yes, Arpita, great. MOSFET is on because minus 1 is less than minus 0.5. In PMOS, you should be less is important. Great. So this completes my second example problem. Now triode effect I'll explain for you. A triode region. Next concept is triode effect. One is in ohmic, and second one is also in ohmic effect. So if you are completed, please give me a message so that I can go for the model 3. After your completion, just post in the chat so that I can understand who is completing or not. Properly write in the notes, take a sufficient time to write, then after that give a message so that I will proceed for the triode region examples. Great, Swati, Shavanidas, great, Kamlesh, great. Boss, done, good. Let us go for next example. Let us go for the next example. Next example I am doing. Keep the heading triode region. We'll take an example of can take this as an example for the triode effect. You take threshold voltage as 0.4 volts here. Threshold voltage you take 0.4. You take this as a 2 volts. This as 0.5 volts. This as 1 volt. You take like this. 2 volts, 0.5 volts, and this 1 volt. In a similar manner, we'll go for PMOS question example. Similar example, PMOS. Your threshold voltage, you take it as minus 0.4 volts and make a PMOS question. PMOS problem we are doing. In the PMOS, I'm giving this as 1 volt, this is 1.5 volts, this is 2 volts. You try to solve this problem by yourself. Yeah, Rahman, generally, millivolts means how much millivolts you get confusion in the exams. That's why what they'll do is 0 volts they'll design for ohmic. Okay? Always they'll design for 0 volts as ohmic effect. If any order of volts, 0.6 volts, 0.8 volts like that you got, you can call it as triode region in electronics. Okay? You can just say triode. So millivolts means how much millivolts we don't know. The value of boundary, correct? That's why they'll design 0 volts. So easy to catch the ohmic region. Other than 0, anything comes, you can just orally, you can say triode effect. So you can see in this problem, what is happening? Carefully see. This is gate, this source, this is drain. So VGS is here, drop. This is your VDS. First VGS you can find. It is VG minus VS. It is a 2 minus 0.5. It is equal to 1.5 volts. Your gate to source voltage is 1.5. Whether it is on means yes, VGS is greater than VD we are getting. 1.5 is always greater than 0.4. So I think your MOSFET is on. First I will confirm always MOSFET is on or not. I just confirm this point by the VGS knowledge. Okay. After this we'll try to check VDS value. VDS value we are getting it as VD minus VS, which is 1 minus 0.5, which is coming to be 0.5 volts. So I want to know whether 0.5 is in current saturation or in triode region. This is the doubt we'll get. 0.5 is in triode or current saturation. Then how to analyze this topic? Suppose if I assume MOSFET in triode region, suppose. We'll assume it, the condition, if it is in triode, what is the condition should be satisfied? VDS should be less than VGS minus VD. This condition if you satisfy, you are in triode. Otherwise you are in current saturation. So VDS we got 0.5 here is less than VGS we got here 1.5 minus 0.4. So 0.5 is less than 1.1. This statement is correct. So 0.5 will be always less than 1.1. That means the system is working under triode region. So this answer whether it is in triode or current saturation, if you have any doubt, you can assume it may be triode or current saturation, you assume it. If your assumption is correct, triode may correct ho gaya, it's okay. If it is not correct, what happens? You are in current saturation. Opposite you can tell. So like this you can do it. Okay, you can assume triode or current saturation, whatever you like you can do it. So this is the story. So I think your MOSFET is triode. MOSFET is in triode region. MOSFET is in triode region. So in the next case, this is gate, this is source, this is drain. We have VGS voltage here. This is VGS voltage. First VGS we are finding. VG minus VS is 1 minus 2. Answer is minus 1 volt. So VGS is coming less than VD. Minus 1 is less than minus 0.4. Is correct. So MOSFET is on. Here also we are getting MOSFET is on. Not VDS is not less than VDR, my friend. VDS should be less than VGS minus VD. Okay. Then the MOSFET will be in triode region. So this is in triode we are getting answer. Second case MOSFET became on. So what about VDS value here? Your VDS value is VG, VD. It is VD minus VS. VD is 1.5 minus 2. It will be minus 0.5 volts. So VDS we are getting minus 0.5 volts in the class. Here you have been assumed that MOSFET is in triode. There is no rule that I have to assume in triode. You can assume in the current saturation also. Suppose I assume it in current saturation here. Assume MOSFET in current saturation. You can start assuming anything, no problem. Whatever you like you can assume. Okay, whether it's correct or wrong you have to justify. What is the concept here is VDS should be less than VGS minus VD is current saturation. It is not greater, it should be less is current saturation. Here less is triode, then less is current saturation. So answer is minus 0.5 is less than VGS value is minus 1 minus of minus plus 0.4. So minus 0.5 is less than minus 0.6. So we are getting like this. Minus 0.5 is less than minus 0.6 is coming. It's a wrong statement. Because minus 0.6 will be less than minus 0.5, not greater than minus 0.5. So correct answer means you can say that your MOSFET is in triode region. This completes the story of MOSFET that you are studying about the concept of triode effect questions. This is the way how they will design the questions for you. So complete this, we have only one chance. That is current saturation. If I explain, my first analog module is completed, but testing part is completed. Okay? Testing part, smoothly completed concept. Let us have the final analysis. That is called current saturation, we'll see. Last concept is current saturation. So be ready for the last example. That is called current saturation. Current saturation. see your messages. You're all completed. Not only completed, I'm expecting you're understanding the procedures. Correct? You're doing the problems in a good manner. I'm expecting all these questions you're understanding well. Morning say we have done a good work. That's why these questions became easy now. So Rajnish explain to last two line. Last two line is nothing but VDS less than VGS minus VT. We call it as current saturation condition. Okay, we'll forget make now. Conditions go. Less than you are in current saturation, greater than you will be in triode. So condition check your mind. So the testing has become failure. Therefore, if you are not in current saturation, you will be in triode region is my answer. Okay. If you are failure there, you will be in current saturation. So don't worry, just 1 minute. Just 1 minute. I'll change it. Just 1 minute. I think the screen came back. Okay, slightly black screen came for 2 times due to this Wi-Fi I think. So anyway, now it came well. Let us start the final one, and we'll take some small break to start a new video again. That is the final passing class. Okay, now visible. Very good, great. So the last final touch I'll give for the testing. The fourth one will be the final touch called as current saturation. Current saturation. We'll take an example one like this. It's a very special design. Most of the times you see in the workbook problems. So be careful to understand this testing part. Source side I have kept it wrong. And I have given this side is, for example, 4 volts, and just a shorted like this. I want to know in which region this is working. Threshold voltage, you can take this as 0.5 volts for this problem. Take threshold is 0.5, just check this problem. Check this problem. A very interesting design it is in our class, MOSFET. Example 2, I'll go, second example. Example 2 you can see. Try to start doing these 2 problems. So please take these 2 problems. Somebody does obtention area now. If VDS value, if it is not 0 volts, suppose millivolts are or volts are, they'll try to give the options for you clearly. Ohmic, they'll not do triode. If they give triode, they'll not do ohmic. They'll clearly mention that. They'll not confuse you that both the things they'll not do. Okay? Otherwise, particularly they'll use 0 volts VDS value to tell that it's ohmic directly. If the value comes in an order of value, we cannot say millivolts. 0.6 volts, you can write as 600 millivolts. But we'll get confused about that. That's why examiner will write triode or ohmic. Any one option they will be given. You can take according to that. Okay? Both answers literally they'll not try to design it. चलो then एक बार calculate करते हैं. Same triode and current saturation. So let us see. This is your drain. This is gate. This is source. We have VGS here. This is your VDS. First MOSFET is on or off. This passing you can see. VGS is equal to VG minus VS. How much is the drain voltage? Is same as gate voltage here. How much is the drain voltage? Is 4. So gate voltage is also 4 because it's a short circuit. So 4 minus 0 is 4 volts. So you can say that your VGS is greater than VD because VD is only 0.5. This is 4. 4 is greater than 0.5. So you can say that MOSFET is on in this case. First confirmation is over. MOSFET is on. MOSFET is on in the class. But whether it is in triode or current saturation, we'll justify now. Whenever you are making this as short, there is one logic we are seeing is the gate to source voltage and the drain to source voltage will be same. VDS is equal to VGS is coming in this problem. This point is very interesting then. The output voltage drop and input voltage drop is becoming same. So what is VDS if you can solve? VDS how much it is? Will be same as VDS is same as VGS. So it is a VGS is equal to 4 volts. So already VGS 4 we got. That is only VDS in the problem. So assume MOSFET in current saturation, suppose I assume whether this condition satisfy or not. You can check. VDS should be greater than VGS minus VT is your current saturation testing. So we have 4 here. This is 4. VGS is also 4 minus VT is 0.5. So I think 4 here. This is 3.5. So I think this is correct. So MOSFET is in current saturation. So what I want to tell in the class is who will satisfy this condition in our classes? Who will satisfy the condition in MOSFETs? VDS is equal to VGS. I think no need of checking daily in our classes. You can feel that your MOSFET is in current saturation. It's an analog IC designs. One of the popular technique for us for passing classes. Okay. Whenever you see a short circuit between drain to gate, automatically you can tell now 1 volts. The MOSFET will work compulsory in current saturation. No need of doing this much analysis daily in your classes. Okay. In workbook you have so many questions based on the short techniques. So just feel that the question is under current saturation, straightforward. The second one we'll observe. This is your source, gate, this is your drain. This is the situation you are seeing. Okay, this is the situation. So we have VGS here. This is your VDS. VGS. Let us find out first VGS value. It is 1 minus 2. It is minus 1 volt. Your VGS is coming to be minus 1 volt. Your VGS is minus 1. Therefore, VGS should be less than VD. It is on. So minus 1 will be less than minus 0.6. Yes, correct. Minus 1 will be always less than minus 0.6. Correct. So your MOSFET is on. First confirm that it is on or not. It is on. Your MOSFET is on. Your MOSFET is on. Chandramohan, इधर टेबल फॉर्म क्यों चाहिए आपको? टेबल फॉर्म क्यों चाहिए? इधर क्या ये सिंपल पॉइंट्स? VGS greater than VT, NMOS is telling I'll be on, and PMOS is telling less than VT, it is on. उनके लिए टेबल फॉर्म क्यों चाहिए यार? Same rotation and concepts there. एक बार घर जाकर after the class if you sit by yourself at home and you just see this condition and if you study, ये क्या है? Very simple questions. Okay? If you want in short notes, I'll give the table form if you want. When I'm teaching tomorrow problems, I'll give you short notes there, you can understand it. So एक simple table form बना सकता हूँ आपको चाहिए तो वो कल देखते हैं. But they are very easy to develop these concepts. Okay? इनमें tension नहीं लेना, simple problems है. So coming to the final here, VDS will be how much we are getting is VD minus VS is 1.5 minus 2, it will be minus 0.5 volts. VDS is coming like this. So assume MOSFET in current saturation suppose. Then condition is your VDS should be less than VGS minus VD. If you are less than VGS minus VD, you are in current saturation in case of PMOS. So your VDS is minus 0.5 less than VGS value is minus 1 minus of plus 0.6. So minus 0.5 is less than minus 0.4. So minus 0.5 is less than minus 0.4 is correct. So your MOSFET is in current saturation. So with this I have been covered the complete analog first concept called testing part is completed. Okay. If you see the BJT class compared to PJT class, MOSFET class is more enjoyable. Only thing is there will be 3 doubts for you in a MOSFET symbol. We just check the points. Okay. This class is very important for the further concepts in my tomorrow classes and today biasing classes. It is a very important concept. So with this I have been covered my first analog lecture in MOSFET classes. So we'll take a small break, okay, just for 15 minutes and we'll continue the class for biasing class because I have to cut this video and I have to present a new video for you. That's why some time is required for it. So let us take a small relief and we'll finish that biasing class. After that we'll stop the class today. Tomorrow class morning we'll start the problems and remaining concepts will complete. Tomorrow my job is current mirrors I'll complete and one more big hobby is CMOS inverter techniques we have to complete. Okay, these questions who will complete then only the total workbook we can cover. Otherwise you will stuck in my workbook concepts. That's why this all contents I'll cover by tomorrow. You'll be enjoying the workbook if you get this total content. So tomorrow if you complete MOSFET, day after tomorrow onwards we'll start the amplifier classes. Amplifier class will take for 3 days. After 3 days we have completed the total 3 devices in analog. One is diode is completed, BJT is completed, MOSFET. The remaining portion is only op amps, the last lectures. Okay. Op amps itself will take nearly 4 to 5 days class. That 4 to 5 days is completely on the module of op amp designs. With that the total analog you can complete. Lastly for ethical students I promise one day at one end of the day I'll teach you the device portion for you to end up the total analog class. Okay, BJTs and diodes I'll teach because MOSFET already I covered here. Device part. So no need of MOSFET. BJT I'll explain and the PN junction theory I'll explain for you. Pooja Prabhakar, MOSFET biasing, you should not ask like that here. Electrical students and EC students, MOSFET biasing is very important. Okay? Without learning MOSFET biasing, how you do the questions in amplifiers in the exam point of view? So please don't ask like that. If it is not there, then I will tell in the class definitely. Correct? If electrical students suppose that portion is not there, I'll try to highlight in the class. Okay? Don't say like that. MOSFET biasing, if you don't study, there is a meaning of teaching analog electronics in my class. Both important topics, compulsory for MOSFET biasings. BJT biasings already you got the knowledge. The MOSFET is simple compared to that. Okay? Let us take a small break, 15 minutes. It is now 4:10. So around 4:25 I'll start the class. By 5:30 or 6 we are going to close the matter of biasing today. Okay? Today that is the final class today. Maybe 6 we are not closing today also. By 6 only we complete the today module. So if you complete up to here, some students ask me that previous slide, okay, I'll keep it like that and I'll take a break for 15 minutes. I'll take a break for 15 minutes. So whatever the previously when I started my class, this is the slide I kept. So who has missed this slide? When I started my class, some students have not written this slide, please note on it. Okay? Pooja Prabhakar, compulsory MOSFET biasing padna hai. If you don't study that, you are not best for what is amplifier classes. Then you will be gone in doing problem solutions के लिए difficult हो जाएगा. Definitely पढ़ना. Okay? Don't say the word that it is not important. Important ये नहीं बोलना यार. ये पूरा important होते हैं हम teach करते classes. Unnecessarily the word become important, non-important. Syllabus में पूरा नहीं लिखते हो, वो point understand कर. क्या लिखते हो वो हम understand करके teach करते हैं. Okay? So this is the story. A 15 minutes break I'm giving for you. Just 15 minutes. Now it is exactly 4:10. Okay, 4:25 we'll start the class. 4:10 or 4:30 we can start the class. 4:30 p.m. I'll start the class.